Gases. So today we're going to be talking about gases and different gas laws. So talking about gases first brings us up to the discussion of pressure. And what is exactly pressure? How do we define pressure? Very generic, simple definition is that pressure is the force exerted per unit area by gas particles as they strike the surfaces around them. So here in the picture you can see these are gas particles. And the pressure is the force that exerts from this gas particle as it hits the surface. So a gaseous atom or molecule exerts a force when it collides with a surface, resulting in a specific pressure that it would then have. So we can say that pressure is equal to force over area. And there are certain different ways that we measure that. Like a ball exerts a force when it bounces against a wall. Just like an atom exerts a force, like if there's gas in a beaker, it exerts a force as it hits the wall of that beaker, and that's what we think of as pressure. Good example of that would be to think of what happens when you are in an airplane. So we know that the air contains gaseous atoms and molecules in constant motions, and the particles collide with each other and the surfaces around them. And that force slowly builds up. The pressure that a gas sample exerts is the force that results from the collisions of the gas particles divided by the area. So that's how we think of as pressure. So that pressure that's exerted by a gas sample depends on the number of gas particles in a given volume. So if you have more, there'll be more pressure than when you have less particles. So when you fly in an airplane, a small earache develops from the imbalance of pressure externally due to higher altitude and pressure in the ear cavity. So you can see here, there's your normal pressure. And then when you're in an airplane, you've got higher altitude, you're elevated. What happens is that a small earache develops because of the imbalance between the internal pressure and the external pressure. So that since the altitude is so high, that pressure in your ear cavity causes you to have a small little earache. How do we measure pressure? So I wanted to introduce the measuring of pressure before I talk about the units to know exactly where these units come from. So pressure is measured usually in a barometer in millimeters of mercury. So why do we care about millimeter mercury? Why is it not just atmospheres like you've probably seen by now? Well, way back when, using a barometer is how pressure was measured. So you can see here in this diagram, the tip of this evacuated glass tube. So there's this glass tube, and it's evacuated of all its oxygen content. And it's tipped over into a pool of mercury. And it was completely evacuated. There was absolutely nothing in it. No gas particles, nothing. Just completely empty, cleared out, tipped over, and placed into a pool of mercury. And what happens was the atmospheric pressure, since there's always pressure on us, on the surfaces of this mercury, forces the mercury up the tube. So that pressure that's pushing down from the atmosphere, that's pushing on the surface of the mercury, forces the mercury to go up the tube. The density of mercury is 13.5 larger than water. So the atmospheric pressure counterbalances the force of the gravity on the column of the mercury. So then the way that we would measure pressure is we say the height difference between exactly where the mercury stopped to beginning of that pool is the pressure that I have inside. So how can we apply that to calculating the pressure of a sample? Well, first let's look at the units. So a very, very common unit is millimeter mercury for that reason. That's how a pressure was measured, through taking a ruler and measuring the distance just from where the mercury was leveled up in the evacuated tube to where it was started. Usually it was in millimeters. If you see inches mercury or centimeters mercury, it's just using a ruler to calculate the height of the mercury. That's why we think that pressure is millimeter mercury. Now, 1 millimeter mercury is directly related to a torr, also a very common unit. And then the common unit that we see a lot is atmospheres, and they have a relationship of 760. And then you have some other units. So these are really important. Write these somewhere on your notes. Have them handy to you when you're doing different problems so you can get used to the different types of conversions, knowing that these are the very common ones in day-to-day life. So a manometer. This is something that we use a lot in labs to calculate a pressure of a sample. So a manometer is a U-shaped tube, as you can see right here, with a dense liquid that's usually mercury. So mercury, because it's 3.5 times more dense than water, is usually used when calculating pressure. So what happens is you have this sample here, right? This is your gas sample. And you want to know the pressure of it. So you hook it up to a manometer. And one end of the tube, as you can see, is completely open to the atmosphere. And then the other end of the manometer is attached to this gas sample right here. So this is closed. This is attached to sample. And then that one, just like it's labeled, is completely open. So then what happens is that if the pressure of the gas is exactly equal to the atmospheric pressure, so remember that the pressure in the atmosphere is always pushing down. So since that's open, it's pushing down on the mercury, right? So the mercury levels are going to even each other out. So there's the pressure from the gas that's pushing on the mercury and the pressure of the atmospheres. The mercury levels on both sides of the tubes will be the same if they're equal. So notice how in this example, my mercury levels are not the same, right? So if my pressures were equal, my mercury would be up here, but it's not. So the difference in the height between the two levels is equal to the difference between the pressure of the gas and the pressure of the atmosphere. So how we can calculate the pressure of a gas is to find the pressure of the atmosphere and figure out the difference of the height to know exactly the pressure of the gas that we have of this sample. So with all that said, let's just do a little practice problem here. A high-performance road bicycle tire is inflated to a total pressure of 132 psi. What is this pressure in millimeter mercury? So you'd go back and you look for, okay, psi and millimeter mercury. What is my, I'm going forward, what is my unit conversion? Well, I have psi to ATM, and then I have ATM to millimeter mercury. So I know that 1 atmosphere is equal to 14.7 psi, and 1 atmosphere is equal to 760 millimeter mercury. So I take 132 psi times 1 atmosphere over 14.7 psi, which will then cancel out my psi, times 760 millimeter mercury over 1 ATM. Atmospheres cancel. You take the 132, divide by 14.7, and multiply by 760, and you get 6.82 times 10 to the third millimeter mercury. Always making sure you check your sig figs and you have your units. So just getting used to and familiar with the different unit conversions of pressure. So pressure brings me up to a really important subject of this chapter, which is gas laws. So let's think of the 4 basic properties of a gas sample. What does a gas sample depend on? We already talked about it depends on the amount that you have and the space that it's in, right? So that volume and pressure. So a gas sample depends on pressure. But what else can a gas sample depend on? Temperature. So if you think of, if I have a container and it's sealed, obviously, because if it's not sealed, then all my gas samples are going to leave. But if I have this container and that's sealed, and I have these gas particles in it, and they're constantly hitting different walls and going all over the place, I know that by volume, if I have a larger volume, it's probably going to be less force because I have more space for these gas particles to collide with the walls. The number of particles is going to depend on that volume, and then the pressure. How does temperature relate? So what would happen to these gas particles if I cranked up the temperature, if I made it a lot hotter? Well, if I'm making something hotter, I'm providing energy. And what would that do to these particles? They would have so much energy that they would just go even faster, right? Creating more of a pressure. So all of these things are kind of interrelated. And what we can do is we can sometimes hold certain variables constant and see how two variables are just directly related to one another, which is the simple gas laws. The properties that are interrelated, how one affects the other, is how we get to the simple gas laws. So the first one is Boyle's law. We're thinking of just volume and pressure, which means what are we holding constant? The amount, so moles, and temperature. And Boyle's law is the inverse relationship between volume and pressure. So we say V1 P1 is equal to V2 P2. So look at my little diagram down here. I have a volume of 1 liter and a volume of 0.5. Notice how at the volume of 1 liter, which is bigger than 0.5, you have the gas particles going around, right? And again, pressure is that force that's exerted as the particles is hitting the container or the sides of surfaces of whatever it's in. 1 atmosphere. So then if I push down, right, I'm decreasing the volume. If I'm decreasing the volume, what that means is I'm closing the space for these gas particles to go around. So they don't have nearly as much room. So they're going to hit the walls of the container a lot more because they have less space to go around. Well, if they're hitting the surfaces of the container more, what happens to their pressure? Well, as you can see, the pressure goes up. So as your volume is going down, your pressure is decreasing and vice versa because it's completely related, thinking of, how little spaces you have to move around towards big spaces you have to move around. Next is Charles's law. So Charles's law, we look at the relationship between volume and temperature, holding pressure and the amount of moles constant. So suppose that we keep pressure and the amount of moles constant, looking at volume and different temperatures. That's Charles's law. And they're directly related. So let's think about that exactly. So the volume of a gas will increase as the temperature of a gas increases. So here in my little example, when temperature is increased, molecules will move what? Are they going to move faster, slower? What's going to happen to them? They're going to move a lot faster. And if they're moving faster, they're going to hit the sides of whatever container they're in even faster, right? So if you have a balloon and you're filling it up with air, right? You have oxygen molecules in this balloon. And if you are putting this balloon on hot boiling water, that's adding temperature, increasing heat. And those particles inside this balloon are going to hit the sides harder, causing an increase in volume. Because think about it. If they're hitting the walls, and I held pressure constant, right? And these particles are constantly hitting this balloon, the balloon's going to start to expand. It start to get bigger and bigger because these molecules are hitting the surface. So when the temperatures increase, because the particles start to move faster, it forces that surface to expand a little bit. So it forces the volume to get larger. And let's think the inverse of that. So when the temperature is decreased, molecules move a lot slower, right? So they're going to go the other direction. Not really going to hit the sides of the container as much. Faster. Not really doing much to the volume, but then slowly starting to shrink it. So think of what would happen to a balloon if you put it on ice water. Right? The molecules, because they're not moving fast, they're going to move even slower. Nothing's really holding up the sides of the container for it to then slowly shrink down. But the pressure, because we're holding it constant, is exactly the same inside and outside. So we have V1 over T1, because it's a direct relationship, is equal to V2 over T2. Let's think of volume and the number of particles holding constant the temperature and the pressure. So what happens when the amount of gas changes, right? So now we're taking particles away or adding more particles. The volume of a gas sample at constant temperature and pressure is a function of the amount of gas in moles. So we're thinking of volume and particles in moles. They're also directly related. So you can look at this little diagram here and see that as I increase my number of particles, right, I'm increasing my volume. Kind of the same idea as my little balloon example, because if I'm pumping in more particles And those particles are going to hit the walls of the container. They're going to expand the volume. When you're blowing up a balloon, either with helium or with, you're just doing it yourself with your own oxygen, the more particles you're adding, the more oxygen particles you add to this balloon, what happens to it? It doesn't just stay still, the balloon expands. And then when you let particles out, the balloon shrinks. So they're completely related. As the volume increases, so does the particles of moles. So at constant pressure and volume, the volume of a gas is equal to the number of moles of a gas. So this is at constant pressure and temperature, a little typo here. You can see that we'll talk about these values a little bit more in a second, but they're completely constant, thinking of what just happens to the particles and the volume. Now, one more law for now, as part of the simple gas laws, I always like to include this here, is when you have everything together, but we're not changing the number of particles. So let's just say the number of particles stays the same. How is the pressure, volume, and temperature of a sample related? So this is the combined gas law, and it's a little weird to look at here, but it's just P1V1, that relationship over T1 is equal to P2V2 over T2. So you can see that as the pressure and the volume go up, the temperature is also related to them exactly. However, what's one more law, one more relationship that we haven't looked at yet? Pressure and temperature. So Gay-Lussac's law talks about the relationship of pressure and temperature holding volume and the amount of moles constant. So if I'm increasing my temperature, again, these are all kind of interrelated, right? My particles have so much kinetic energy that they begin to move around faster. Well, since they're moving around faster, they're hitting the sides of the container with a lot more force because they're just faster. Just like you throw a ball against the wall, but you're adding speed to it, it's going to really make a loud sound because it's hitting it so hard. So therefore, you're increasing your pressure. This then relates up here to the combined gas law, kind of putting everything together. So from that, we then have something called an ideal gas law. So an ideal gas law is an equation that was formed by different chemists in the past to show the behavior of when a gas is behaving ideally, right? For just certain things of what we want. Well, to make this gas or sample behave ideally, scientists had to create a gas constant so that proper units are canceled out depending on what you're looking for. So the gas constant is 0.08206 atmospheres, liters, mole, Kelvin. And the way that the gas constant was formed is to put everything under standard conditions, to make your pressure 1 atmosphere, your volume 22.4 liters, your moles 1, and your temperature at 0 degrees Celsius, 273 Kelvin. So when all of these factors were placed in, they were able to determine the gas constant, saying a gas is behaving ideally. So the previous gas laws can be derived when these two different variables are held constant to help us understand the ideal gas. With that said, let's look at some applications. So chemists agreed to a set of conditions to report as measurements. Standard temperature and pressure. So you'll see STP a lot in your homework or future. And what that means is things are in standard conditions. So you may be seeing problems where not given any information, but it says STP. Well, STP actually gives you a whole type of information that the temperature is at 0 degrees Celsius, which is 273 Kelvin, and the pressure is at 1 atmosphere. So basically, chemists came together a long time ago and said that these are the standard set of conditions that we like to report for gases. And for 1 mole of gas at standard temperature pressure, the ideal gas equation is then 22.4 liters. So again, when you plug things into the equation, you see that at these standard conditions, I have this standard volume. So applying the ideal gas law, we can determine that the molar volume of an ideal gas is at STP is 22.4 liters for 1 mole, and we know that 1 mole is 6.022 times 10 to the 23rd molecules. I do want to point out that molar volume, because it has that word molar in it. It's not just liters, but it's liters mole, right? So you'd still have to worry about getting rid of your moles. Moles is always that amount of particles. So just really fancy wording for saying these are our standard conditions. 1 atm, 273 Kelvin, 1 mole of gas, and 22.4 liters. Here you can see the standard conditions. It doesn't matter the different sample that you have. I mean, the size of helium, xenon, and methane are all different, but 1 mole of each at STP give you the exact same volume. It doesn't matter on any size. So that's why these were created, to create a set of standard conditions that all gases can apply to. Let's practice. So calcium carbonate, the principal compound in limestone, decomposes upon heating to calcium oxide and carbon dioxide. A sample of calcium carbonate is decomposed, and the carbon dioxide is collected in a 250 milliliter flask. After decomposition is complete, the gas has a pressure of 1.3 atmospheres as a temperature of 31 degrees Celsius. How many moles of carbon dioxide gas were generated? Okay, long question. I already kind of forgot where I was. So if I'm looking at my first sentence, calcium carbonate, the principal compound in limestone, decomposes upon heating to calcium oxide and carbon dioxide. I'm going to write my equation. So calcium carbonate decomposes to calcium oxide and carbon dioxide. Now let me see. Am I balanced? 1 carbon, 1, 2, 3 oxygens on the right, on the left, 1 calcium. Perfect. So I have a sample of calcium carbonate that's decomposed, and then the carbon dioxide is collected in a 250 milliliter flask. So I'm given my volume of carbon dioxide. After decomposition is complete, the gas, which is the carbon dioxide because everything else is solid, has a pressure of 1.3 atmospheres. And a temperature of 31 degrees Celsius. How many moles of gas were generated? So you want the moles. So do I need to worry about using my equation here? Well, I have my volume of my carbon dioxide, I have my pressure, I have my temperature, and I'm looking for my moles. Now that you have all those gas laws, what I always like to do is, if I have them all written next to me, so here's my Boyle's law, here's my Charles law, Gay-Lussac's law, Avogadro's law, combined gas law, and then my ideal gas law. So all my little gas laws. What can I use here to solve this problem? I'm looking for the moles. Well, if I'm looking for moles, I need to have moles in it. So maybe use this and this. And I have only 1 volume, 1 pressure, and 1 temperature. So I use my ideal gas. So PV is equal to nRT. I have pressure, volume, temperature, and I always have my gas constant. So then you can isolate in your equation and find that the moles will equal the pressure times the volume over R constant times temperature. Now remember, your R constant is 0.08206 liters times atmospheres over mole Kelvin. So you have to make sure, since you want to get moles here, that all your other units cancel out. So you have to make your conversions to get the proper units. So 250 milliliters divided by 1,000, right? Will give you 0.250 liters. The atmosphere is already the way you want, but then temperature, you have to add 273.15 Kelvin to get 304.15 Kelvin. And now you have everything you need. So then pressure is 1.3 atmospheres. Volume is 0.25 liters. divided by gas constant, 0.08206 liters, atmospheres, mole, Kelvin, times 304.15 Kelvin. Liters cancel out, atmospheres cancel, Kelvin cancel. You're left with moles, and that's 0.013 moles of carbon dioxide, and then you're done. So it's always really important to write the units of the arc constant because it's kind of a good reminder of what you want your units in. The question arises a lot of why not just convert your gas constant, and there's no reason, you totally can, but I just think it's always good to keep the constant the way that it is and convert everything else to how you want the units to be, so you can visualize exactly that they cancel in the form that you want, so you get the unit that you want in the end. Alrighty. The gas pressure in an aerosol can is 1.5 atmospheres at 25 degrees Celsius. Assuming that the gas obeys the ideal gas equation, what is the pressure when the can is heated to 450 degrees Celsius? So you think, oh, okay, I need to use ideal gas law right away. Duh, that totally makes sense. But let's look at this again. So the gas pressure in an aerosol can is 1.5 atmospheres. So I'm given P1 is 1.5 atm at 25 degrees Celsius. Well, that's my first temperature, 25 degrees Celsius. This presumes ideal gas law. So that doesn't mean necessarily that you have to use the ideal gas equation. What it does mean is that this equation can be derived from the ideal gas. This sample, I should say, is behaving ideally. What is the pressure? So you want another pressure, so I'm going to say P2, when the can is heated to 450 degrees Celsius. So through the ideal gas equation, we were able to visualize in the combined gas law the relationship between pressure and temperature. So since I want pressure 2, I know that pressure and temperature are related through Gay-Lussac's law. So then one of two ways that you can do this. You can rearrange your equation, or you can plug everything in and then solve for what you want. So I have 1.5 atmospheres over 25 degrees Celsius is equal to the second pressure over 450 degrees Celsius. Question comes up a lot. Do you have to convert here? You don't necessarily need to, since your Celsius will cancel and you'll be left with atmospheres. So I would usually just leave it exactly the way that it is. So then you can cross multiply 1.5 atmospheres times 450 degrees Celsius is equal to 25 degrees Celsius and the second pressure. You then would divide your 25 degrees Celsius on both sides, and then you can see your 25 degrees Celsius will cancel out the Celsius from the 450, and your pressure would be 27 atmospheres, and you would want 2 sig figs. Let's look at one more, practice one. So a gaseous hydrogen and carbon containing compound is decomposed and found to contain 82.66% carbon and 17.35% hydrogen by mass. The mass of 158 milliliters of the gas measured at 556 millimeter mercury and 25 degrees Celsius was a 0.75 gram sample. So that's the mass. What is the molecular formula of the compound? So what we're looking at now is a little bit of a review. So we're putting a couple different things together. So you're given that a sample that has hydrogen and carbon in it is made up of these percentages by mass. So that actually means that I have 82.66 grams of carbon and I have 17.35 grams of hydrogen. And I have the mass of my sample is equal to 0.275 grams. I have that the volume of the sample is 158 milliliters. The pressure is 556 millimeter mercury. And then the temperature is 25 degrees Celsius. I want molecular formula. So I know that molecular formula is found by multiplying N times the empirical formula. So I need to figure that out. Okay, well, how would I do that? Let me just organize. Given. Okay, well, let's just go up here. So 82.66 grams of carbon and 17.35 grams of hydrogen. What can I do with that information? Well, I know molar mass. I can find moles, right? Because empirical formula will tell me my lowest ratio of the amount of moles of carbon I have in my sample and hydrogen. So if I take my carbon and divide by its molar mass, I get 82.66 grams divided by 12.01 is 6.88 moles carbon. And then I can do the same thing for hydrogen. And that's equal to 17.212 moles of hydrogen. And now what's my next step? Are those the moles that I would use in my equation? Since my empirical formula is my lowest ratio, I have to then divide by my smallest number. So then what's my smallest? 6.88, divide both sides by 6.88. And I would get 1 mole carbon and 2.5 moles of hydrogen. So I have C1H2.5. Would I leave my empirical formula like this? Nope. You do not leave a decimal in that way. So what you have to do is multiply the whole thing until you get rid of the decimal. Well, if you multiply the whole thing by 2, you would get C2H5. And this is your empirical formula. So remember, your molecular formula is the N times the empirical formula. What does that N stand for? It's the molar mass of the sample divided by molar mass of empirical formula. So can I find my molar mass of my empirical formula? Yep, because I would just take my 2 carbons plus my 5 hydrogens. That would be 2 times 12.01 plus 5 times 1.008, and that is equal to 29.42 grams per mole. Wow, my pen just got really thick there for a sec. Awesome. I'm going to do a little line here so we don't get too confused. So I already have this bottom part. I have the 29.42 grams per mole. How can I figure out the molar mass of my sample? Well, I'm given certain information of my sample if we go back to this chunk of numbers. I'm given my mass and the volume, the pressure, and the temperature. Well, I know molar mass is equal to grams over mole. So I need moles to find the molar mass. If I have pressure, volume, and temperature, can I find moles? Yep. PV equals nRT, and will then be PV over RT. Awesome. I have all my values so that I can find the moles. However, you have to make sure that all of your values, again, associate with our constant, 0.08206, liters, atmospheres, mole, Kelvin. So you can separately convert everything like we've done in the previous problem. Or sometimes going to show you a different method. You can plug everything and your conversions into one big equation. So my pressure, 556 millimeter mercury. I would convert 1 atm over 760 mercury times my volume. My volume would just be divided by 1,000, so 0.158 liters. Divide that by the R constant, 0.08206 liters, atmospheres, mole Kelvin. And the temperature, which would be 25 degrees Celsius plus 273.15 Kelvin. All your proper units would cancel. You'd plug it into your calculator and you'd get 0.00472 moles. So then the molar mass would be I'm going to write it up here because I'm running out of room. Molar mass is then this mass of the sample, which is 0.275 grams divided by 0.00472 moles. And that gives you 58.51 grams per mole. And plug that in down here, 58.51 grams over mole. That's equal to 2. So then your molecular formula will be 2 times your empirical formula, which is then C4H10, and then that is your answer. So doing 2 whole different concepts, applying the ideal gas law to empirical formula, molecular formula, and percent by mass. So lots of different types of concepts. Note that even when the first part of it doesn't really ring a bell and these are really long sentences and it's a long problem, just kind of take it step by step. I first read everything and kind of wrote my numbers down and looked at what I wanted. And then I thought, okay, well, what is molecular formula? The way that I know how to solve molecular formula is I have to find the n, right? The number that an empirical formula is reduced by, and multiply it to the empirical formula. Well, that means I need n and I need an empirical formula. N is the difference between the mass of the sample, the molar mass, and the molar mass of the empirical formula. The way that I can find empirical formula is I take the masses of both, divide by the molar mass, and get the moles. Use the lowest ratio to then get my empirical formula, which is what we did. We had to do a little extra step because you don't want a decimal. You have to multiply through until you get all whole numbers because we don't ever have a half of any type of atom. And then I realized, well, how do I get the molar mass of my sample? I am given all of these components, the pressure, the volume, the temperature, and I know that since this is a gas sample, I can apply ideal gas law to then find the moles, use that with the mass and get the molar mass, find N, and then get my molecular formula. So this brings us up, we already kind of did this in the problem, applying molar mass and density of a gas, but we can also solve for other different components to ideal gas law. You can apply a bunch of different things. So the density of a gas can be the molar mass of the gas, the mass of the gas over the molar volume. Since both of these have moles and then the moles would cancel out. Let's figure that out through calculating the density of nitrogen gas at STP. What's STP? Well, let's first think of what's density. So density, I just clicked ahead. Density is equal to mass over volume. And molar density is moles over volume. I know that my ideal gas is PV is equal to nRT. And since I can apply my molar volume to be moles over liters, and if I used molar mass, applied molar mass into my ideal gas law, that would be grams over mole, I would get grams over liters. So that means that if I wanted to get density in my ideal gas equation, I would have to apply molar mass. So molar mass and density have to be related. Therefore, if I want my density, this is my little sign for my density, it would equal the pressure times the molar mass over R times T. This is because what happens is you have PV over nRT. You would divide over your pressure on both sides. You would get volume as nRT over P. And then you would divide by the moles to get V over N is equal to RT over P. Well, we then would want to get volume over we want the volume to be on the bottom, so you flip both of these, So moles over volume over pressure over RT. And then how can we get the density? So the density is mass over volume, so if we apply molar mass, we can then end up getting rid of the moles, since molar mass, the moles would be on the bottom, and just get since the R is on the constant with the volume, grams, because grams wouldn't cancel, moles would be here, volume would be here, we would end up getting grams over moles. So how can we apply that here to this equation? So if I want to calculate the density of my nitrogen gas at STP, well, I'm not given any information except for that I want density. What's STP? That means my pressure is 1 atmosphere, my temperature is 273 Kelvin, my volume is 22.4 liters, and my moles is 1 mole. So PV is nRT. Also, the density is equal to pressure times molar mass over RT. So my pressure is 1 atmosphere. My molar mass of nitrogen gas is N2, so it's 28.02 grams per mole, over my R, 0.0821 liters atmospheres, mole Kelvin. Now you see moles cancel out. Whoops. Atmospheres cancel. You'll be left with grams over liters because 273.15 Kelvin will cancel out your Kelvin. So let's just take a moment to plug all of that in. And what would we get? So 1 times 28.02 is the same number, divided by 0.08206 times 273.15, 1.25 grams per liter, N2. Awesome. Let's try one more. So calculate the density of a gas at 750 torr and 27 degrees Celsius if 0.25 moles weighs 9.988 grams. So we have pressure, we have temperature, and we have mass. So this one's a little bit different. So I want density, which means I want grams over liters. I'm given my grams. So what I can do this time, and I have given my moles here, I can do this time is I can use my ideal gas law to get the volume. Because since I have the mass and all the other variables, if I find my volume, I can then get my density. So I bring these two problems to show you the two different ways. The difference between the first is I'm not given moles, right? I'm not given moles or grams. I have to use my molar mass because it has both of them in it. Here, I'm given mass and moles. So I use my volume and all the other variables to find it to then get the density. So I plug my values in. Do I have to convert here? Well, my R, 0.08206. My temperature is not in Kelvin, so you would convert that and divide by your pressure. 755 torr times 1 atmosphere over 760 torr. And then you'd plug everything in to get your volume. So let's do that for a moment. So 0.25 times 0.08206 times 27.5 times 0.250. Divide that by 755 over 760. Remember to keep things in parentheses. 6.19 or 6.20, so 6.19 liters. So then my density is mass over volume, which will be 9.988 grams over 6.19 liters. And then I would get 1.64 grams per liter. You can leave it in grams per liter because it doesn't tell you or indicate to convert to milliliters. But, however, we would actually want this to be 1.6, because 4 is less than 6 for our proper sig figs, because 27 only has 2 sig figs. Awesome. So one more little thing for this segment is to apply molar mass to a gas. So again, we've kind of already looked at this because we've looked at deviations of the ideal gas, how it can be applied with our percent by mass and molecular formula problem, we can use the ideal gas law to determine molar mass. We know that molar mass is equal to grams per mole. And in the ideal gas law equation, you have the moles, you have the volume, and you have the pressure, the R constant, and the temperature. So you can always find your moles if you have mass and divide. You can also use the density, if you have density given, to find the molar mass. A couple different ways that you can do it. Best way is to apply the problem. So just like with the density, you can plug it in or you can separately find variables to then find density depending on exactly what you're given. Calculate the molar mass of a gas with a mass of 0.311 grams. So I'm given my mass here that has a volume of 0.225 liters at 55 degrees Celsius and 886 millimeter mercury. So I'm given my mass. I have my volume, my temperature, my pressure. And I want molar mass. Well, molar mass is grams over mole. I already have my grams, I just need my moles. Since I'm given one volume, temperature, pressure, and I need moles the unit, I know I have to use my gas constant, so PV is equal to nRT, where then N would be pressure volume over RT. Then you plug everything in. Again, you can always separately convert or convert together at the same time. Volume is already converted. Divide by R constant, 0.0821 liters, atmospheres, mole, Kelvin times temperature. Awesome. This will give you, if you plug everything in, 0.009745. And then since you want molar mass, that will then equal 0.311 grams over 0.00974 moles. Your units shouldn't cancel because you want them to be in molar mass units. 31.9 grams per mole. For 3 sig figs, you want 2, so 32 grams per mole would be your answer. So here we separated the two equations, the equation of molar mass and ideal gas law, because you were given mass and then you just need moles. If you weren't given mass, but were given density, then you could use a different type of derived equation that we've already done to apply it here. So all the different concepts that we've learned up to this point can actually apply to the gas laws, just kind of breaking things apart step by step.